Round trip time estimation and timeout. We know that TCP uses a timeout or retransmit mechanism to recover from lost segments. The timeout should be larger than the connection's round trip time, that is RTT, round trip time, RTT. That is the time from when a segment is sent until it is acknowledged. Otherwise, unnecessary retransmissions would be sent. Okay. Estimating the round trip time RTT. The sample RTT, denoted sample RTT, for a segment is the amount of time between when the segment is sent and when an acknowledgement for the segment is received. At any point in time, the sample RTT is being estimated for only one of the transmitted but currently unacknowledged segments, leading to a new value of sample RTT approximately once every RTT. Also, TCP never computes a sample RTT for a segment that has been retransmitted. It only measures sample RTT for segments that have been transmitted once. The sample RTT values will fluctuate from segment to segment due to congestion in the routers and to the varying load on the end systems. Because of this fluctuation, any given sample RTT value may be atypical. In order to estimate a typical RTT, we are taking some sort of average of the sample RTT values. TCP maintains an average called estimated RTT of the sample RTT value. Upon obtaining a new sample RTT, TCP updates estimated RTT according to the following formula. That is, estimated RTT equals to 1 minus alpha to estimated RTT plus alpha into sample RTT. Okay. So this one is new estimated RTT and this one is previous estimated RTT, where alpha equals to 0.125, that's 1 by 8. Substitute this alpha, that is alpha equals to 0.125 in the above equation. We get estimated RTT equals to 0.875, 1 minus alpha, that is 0.875, 1 minus 0.125, estimated RTT plus 0.125 sample RTT. Okay. Note that the estimated RTT is a weighted average of the sample RTT values. Okay. And more recent samples better reflect the current congestion in the network. In statistics, such an average is called an exponential weighted moving average. Exponential weighted moving average, that is EWMA. Figure shows this figure, the sample RTT values and estimated RTT for a value of alpha equals to 0.125, and it shows clearly the variation in the sample RTT are smoothed out in the computation of the estimated RTT. See here, this one is sample RTT and this one is the estimated RTT. So RTT in milliseconds, time in seconds. Okay. The RTT variation is given by div RTT equals to 1 minus beta into div RTT plus beta, sample RTT minus estimated RTT, magnitude of sample RTT minus estimated RTT, where div RTT is an estimate of how much sample RTT typically deviates from estimated RTT. If the sample RTT values have little fluctuation, then this div RTT will be small. On the other hand, if there is a lot of fluctuation, that this div RTT will be large. The recommended value of this beta is 0.25. Okay. Next, setting and managing the retransmission timeout interval. We know that TCP's timeout interval should be greater than or equal to estimated RTT, or unnecessary retransmission would be sent. But the timeout interval should not be too much larger than the estimated RTT. Otherwise, when a segment is lost, a TCP would not quickly retransmit the segment, leading to a large data transfer delays. It is therefore desirable to set the timeout equal to the estimated RTT plus some margin. The margin should be large when there is a lot of fluctuation in the sample RTT values, and it should be small when there is a little fluctuation. Therefore, the retransmission timeout interval is given by timeout interval equals to estimated RTT plus 4 into div RTT. An initial timeout interval value of 1 second is recommended. Also, when a timeout occurs, the value of a timeout interval is doubled to avoid a premature timeout occurring for a subsequent segment that will soon be acknowledged. However, as soon as segment is received and estimated RTT is updated, the timeout interval is again computed using the above formula. Okay. Thank you.